Hi everyone, we're going to continue through graphing some rational functions. Things are going to get, I think, a little bit more interesting here. So hopefully we've caught on to the fact that it's always good to get these things in factored form. So let's go ahead and just start here. The top is factorable, x plus 2, x minus 1 over x plus 3. Okay, so nothing cancels. So we can start our list. We can say wholes. There are none. Zeros. We want the top to be 0 and the bottom to not be 0. So at -2 and 1, -2, y is 0. At 1, y is 0. Vertical asymptotes happen if the bottom is 0 and the top is not. So in this case, at x equals -3. And then global behavior, we want to know if we have a horizontal asymptote or a slant asymptote. So here we want to look at degree, and what's going on is the top is second degree and the bottom is first degree. So this is the first one we've run into where the top wins. If we're plugging in something like 1,000,000, the top is in the ballpark of 1,000,000 squared. This is pretty negligible. The bottom's only 1,000,000. So if you reduce that, you're still going to have 1,000,000. The top is significantly bigger than the bottom, which means this thing's going to head off to plus or minus infinity. So this goes to plus or minus infinity as x goes to plus or minus infinity, which means we don't have horizontal asymptotes. Let's see if I can write infinity here. So this time we're finally going to run into a slant asymptote. There's other possibilities, but I'm only going to look at horizontal and slant. So basically what happens is if the top is 1 degree higher than the bottom, then the global behavior will be linear. If the top was 2 degrees higher than the bottom, the global behavior would be quadratic. So whatever the difference between the degrees is, that'll determine your global shape. So we're just going to be happy with looking at linear global behavior, but it really doesn't change the strategy or the general idea if you have bigger differences between powers. So yes, this has a slant asymptote, but we have to actually rewrite it another way. So we have this standard form, we have a factored form. And if we want to see the slant asymptote, we have to write it in a, what do I want to say, in a mixed number form, basically. So this is like an improper fraction. Degree of the top is bigger than the degree of the bottom. So if you think about things like 3/2 is an improper fraction, 1/2 is a mixed number. Mixed number form of this thing is easier to see global behavior in. So we're going to try and do this, but with polynomials. So if you haven't already, you might want to watch the polynomial long division video and try a little bit of that practice. We won't do any that are too messy, but you will need to be able to do some polynomial long division. So we'll walk through it here. We want to divide x squared plus x minus 2 by x plus 3. So what you're trying to do is make the first term match up. So you would say, what do I have to multiply x by to get it to turn into an x squared? And the answer is just an x. And then you have to do that to the whole thing. You can't actually just multiply the x. You have to multiply the 3 as well. So you get an x squared plus 3x. And then when you subtract, the x squareds go away. Be really, really careful. You're subtracting the whole thing. This is the number one mistake I see. So this is going to be an x minus 3x. So we get a -2x. And then if we have two terms here, we need to always be looking at two terms over here. Oops, dropped it to the wrong spot. So we want to drop down the -2 so that we have a second term. So now the question is, what do I have to multiply x by to get a -2x? And the answer is -2. And once again, you have to do it to the whole thing. So you get a -2x minus 6. And then you subtract, again, subtract the whole thing. So -2x plus 2x goes away. That's a good sign. If that first one doesn't go away, you've done something wrong. -2 plus 6 is +4. Okay, so there's nothing left to drop down, which is looking like a hint that I'm done. The other hint that I'm done is, what do you multiply x by to get 4? The answer would have to be a 4 over x, and we don't want to get into fractions like that with our division. So as soon as the degree of your remainder is smaller than the degree of your divisor, you're done. Okay, so here's the question. What is this really telling us? This is telling us that this this rational function that we started with is exactly the same as an x minus 2 with a remainder of 4 that would still need to be divided by an x plus 3. So that's what long division is telling us. And this form is useful for global behavior because now the remainder part will always be a proper fraction, meaning the degree of the bottom will be bigger than the degree of the top. So if you're plugging in 1,000,000 or 1,000,000,000 or 1,000,000,000, this fraction is going to go to 0. So it's absolutely part of the equation, and it will make differences in the way the graph looks when your x's aren't really, really big numbers. But when your x's are really, really big numbers, this fraction just kind of disappears, and your graph is going to behave like a y equals x minus 2. So long division, and then whatever you get here, ignoring the remainder, because the remainder should go to 0 for large x's, that will give you your slant asymptote. Okay, so let's see. I can sneak it in over here. No holes. Zeros at -2 and 1. Vertical asymptote at x equals -3. And then slant asymptote y equals x minus 2. That's a line. That's a line with a slope of 1 and a y-intercept of -2. So it's going to cross. Slope of 1, y-intercept. Yep, okay. So it's going to go over 1, up 1. So it should cross at x equals 2 as well. Just continue. Ooh, I might need more room. I think I do need more room. So what's going to happen here, this gets a little confusing for people. On either side of your vertical asymptote, you should have something. But that's not true for the slant. You shouldn't have something above and below the slant over here because that wouldn't pass a vertical line test. So yes, you want to make sure you get something over here on the left, and you want to make sure you get something on the right, but again, not above and below the slant asymptote in the same section, or it won't pass a vertical line test. Basically, here's what I would say you should think. You should think if I had a 1 over x type shape, or it could be a 1 over x squared type shape, and I took the horizontal asymptote and I tipped it, I would either get something that looks squashed kind of like this, or I would get something that looks, if we tipped it down instead, really stretched out like this. So these are the kind of shapes we get to see. Again, it should just look like you had a horizontal asymptote and then you tipped it and it either squashed or stretched this thing out. And I'm going to say this one is the squashed one, and the reason why is because I don't have any x-intercepts out here, so I never cross the x-axis, which makes me say I think I should start, you're going to start with arrows really close to this, as always, really close to your global behavior. I think I should start here, and then I can't go up and cross, so what's going to happen is I'm just going to stick close to this thing for a while, and then as my x gets smaller, I'm going to start to drift away, and the vertical asymptote's going to take over and send me to negative infinity. This asymptote, where was it, has multiplicity 1. So on the right-hand side, you should do the opposite. And then we have an x-intercept. So we cross through, again, multiplicity 1 on both of those. And then the next thing is another intercept. So we're going to cross through. And then no more local behavior, so that slant asymptote is just going to take back over. We're going to head off that way. So the kind of squished version, and again, it can be this direction or it could be an upside down version of this direction. But that's the kind of things you expect to see with slant asymptotes. They either look little and squashed, where they fit in here and here, or they look big and stretched out versions of these things. So it would go this way and this way. And your zeros and other information, if you have a hole, should help you figure out which of the two it is. As always, if you're getting stuck, you can plug in a couple more points. I think there was one more thing I was going to say on this one, but it's escaping me right now. Oh, I know what it was. Just like with when you have two vertical asymptotes, you can get that little U shape in the middle, and sometimes it's way down low. So on your graphing calculator, if you check, you might not see it. The same can happen with these. This might be way, way down here somewhere. So I am not worried about vertical scale being perfect, but I do want to see that you know there's something of this sort of general shape down here. Okay, let's look at the next one. So I'm going to go for factoring first. I can factor out a 2x on the top, and I get an x squared minus x minus 6. The bottom is a difference of squares, so I'll just break that up. X plus 2, x minus 2. Okay, let's see. The top, x plus 2, x minus 3, x plus 2, x minus 2. Okay, so this one has a hole. I'm going to cancel that out. I'm going to say this is going to look just like a 2x times x minus 3 over an x minus 2, except I want to make sure that I leave out x equals negative 2. So there will be a hole at x equals negative 2. Ooh, I'm going to get scrunched here. I have too much work to do. Let's see, I'm going to make my list over here. Holes. There is one. The x coordinate is negative 2. To get the y coordinate, we'll plug in here. So we'll get a negative 6. So we'll say y does not equal negative 6 times negative 5 over negative 4. So let's see. It's going to end up negative. And then I'm going to cancel out a 2. So this is 3 halves. So 3 times negative 5, negative 15 over 2. Negative 15 over 2, which is what's negative 7.5. Zeros. The top is 0 if x is 0 or 3. So 0, 0, and 3, 0. Vertical asymptote is at x equals 2. And then horizontal versus slant, again here the degree of the top is, here we can look at either one. So up here the degree of the top is 3 and the degree of the bottom is 2. Down here it's 2 and 1. So either way the top wins, which means this is going to be a slant asymptote. So we'll say horizontal asymptote, none. Slant asymptote. And to find it we will have to do long division. Once again, the idea is that this equation we started with and this one we ended up with are identical, so you can choose whichever one you want, and I would say it's always going to be a little easier to work with, I think that's fair to say, the reduced version. So I'm going to do my long division here. You will get the right answer if you do your long division with the cubic over the second degree, but it's definitely messier. So I'm going to say I'm trying to divide x minus 2 into, you do want it multiplied out, so 2x squared minus 6x. And then placeholders are really good if you're skipping any powers or anything crazy like that. You can always throw in a 0. So we don't have a constant, I put a 0 for that. If we had a 2x squared minus 6, I'd put a 0x in the middle just as a placeholder. There is video and practice on the long division part if that's something that you're not real comfortable with. Okay, so first thing, if I want to, so the question really is, how many times does x go into 2x squared? But I think the easy way to say this is, what do you multiply x by to get 2x squared? And the answer is a 2x. And then you have to multiply the whole thing, so you get 2x squared minus 4x. When we subtract, the x squared goes away, which is good. If that doesn't happen, you've done something wrong. And then remember, this is a negative 6x plus 4x. Don't mess up your signs, which means I have a negative 2x. And again, this is just a placeholder, but I've said we should always have 2 terms, so that's how you get your second term. Now, if I want to multiply x to get negative 2x, I multiply it by a negative 2, which means I'm going to get negative 2x plus 4, and then when you subtract, that leaves you with a negative 4. So down here, I can even go one step further and say this is equal to a 2x plus 2 with a remainder of negative 4 that still needs to be divided by x minus 2, and I still want to make sure I keep track of the fact that x should not equal negative 2. Okay, so lots going on here. This means the slant asymptote is a y equals 2x plus 2. Again, this is part of the equation, and this will make a difference when you're graphing the zoomed in part, the local behavior part. But when you're plugging in really, really big x's, which is what slant asymptote is trying to tell us, this goes to 0. So for really, really big x's, or really, really small x's, that fraction becomes negligible, and it's just the y equals 2x plus 2. So when we graph this one, we have a y-intercept of 2 and a slope of 2. So we have slant asymptote, y equals 2x plus 2. We have a hole at negative 2, negative 7.5. So it's really important to know whether that hole is above or below the asymptote. And I would say the quickest way to find that is by plugging negative 2 in here and seeing what you get. So the hole is at negative 2, negative 7.5. Here, if we plug in negative 2, we get negative 4 plus 2. So we're getting negative 2. So it's definitely below. The hole is down here somewhere. And then we have zeros at 0 and 3. Okay, and then vertical asymptote at x equals 2. Okay, so right here. All right, so again, the slant asymptote, it's pretty steep this time. It's just telling us where to put our arrows. So we'll see if I need more room to sneak something in here. So your choices are either you're going to have this little skinny squashed version, or you're going to have this big stretched out version. And, do we have a multiplicity? No. Okay, so it looks like we're getting, if we come in near the slant asymptote, we're going to pass through the hole. And 0, 0, let me just look back at it. Where was it? Yeah, no multiplicity. So this is a cross through. Ooh, this is an interesting one. And then we have a vertical asymptote. So we're either going to head up to positive infinity or we're going to turn around and head to negative infinity. Since we don't have any x-intercepts, I'm going to say that's got to be a positive infinity. So I think we're getting the really big, this kind, the really big stretched out kind. And then this asymptote, this was x equals 2, has multiplicity 1, so this arrow should be down here. And then we head up, we cross through, and then we're going to start to follow this slant asymptote. That looks pretty vertical, but it will slope off a little bit and follow that line. Okay, so that's a weird one. That's the stretched out looking shape. And this one is interesting because it does actually cross its slant asymptote, which again is perfectly legal. So sometimes you'll just have to do that. You'll be below and then you cross it and end up above because you have to do that to follow the vertical asymptote. Okay, one more. Let's see. So if we factor out an x on the top, we get an x squared minus 4 over x minus 1. And this factors into an x plus 2, x minus 2, x minus 1. Okay, so we have, let's see, holes, none. We have zeros for sure at 0. Again, don't neglect this x sitting out in front. It does tell you an x-intercept. At -2 and at 2, we have a vertical asymptote at x equals 1. Here we have cubic over first degree. Ooh, so maybe I lied to you at the beginning. I said we would just look at slant, but this one, because the degrees are off by 2, we will actually get quadratic global behavior when we do our division. So this will be, it's okay to call it slant. I think it would maybe get a different name because it's not just a slanty line, but that's okay. I'm not super worried about the vocab. So we will get some sort of not horizontal global behavior, basically, which means we will need to do a long division. Let's see, I don't think I can sneak it in at the bottom. So let's do x minus 1 divided into x cubed. Okay, so this one is a good example of skipping powers. There are no x squared, so I'm just going to leave a little placeholder in there. However you want to do it, you can just leave space. I usually write a 0. And then there's also no constant, so I'm going to leave a little placeholder there. Okay, so first thing, what do you multiply x by to get x cubed? The answer is an x squared. And when we do that, we get an x cubed minus x squared, which we should subtract. And our first remainder, the x cubes are gone, is, remember this distributes a positive x squared. We need a second term, so we're going to drop down to minus 4x. Now to get x turned into an x squared, we need to multiply by an x. So we get an x squared minus x. And when we subtract, the x squareds go away. Minus 4x plus x is a minus 3x. And then that'll be a plus 0. And last one, to turn x into negative 3x, we multiply by minus 3. So we're going to have negative 3x plus 3. But when we subtract, the x's are going to go away, and this is going to become a negative 3. Which means over here, we can say this is equal to an x squared plus x minus 3, not a comma, plus negative 3 as our remainder, which still needs to get divided by an x minus 1. So again, the big thing here is that as x gets really, really big and really, really small, this thing goes to 0. So this is going to determine my global behavior. So I have a quadratic, and I was rude to myself. I didn't even make it a nice one. Let's see, what do I know about this thing? So its vertex, let's go ahead and find its vertex, is a negative b over 2a. So it's at negative 1/2. And if we plug that back in, so that's the x, y is, what are we doing? Negative 1/2 squared, so 1/4 minus 1/2 minus 3. Okay, so I guess we're going to make everything fourths. So we have 1/4, 2/4, and then this 1/4 is 12/4. So negative 14, negative 13 over 4, which is negative 12 over 4 would be negative 3, so it's a little lower than negative 3. Okay, so the vertex is at negative 1/2. Let's say this is negative 1. Negative 3-ish. So somewhere around here. And then it definitely opens up. You could find x-intercepts if you want to. I'm feeling a little lazy, but I do know the y-intercept is right at negative 3, so that gets me kind of a decent start. And again, this is not actually part of the graph. This is the asymptotic behavior. And it should go off this way, doing the same thing. And then we have lots of zeros. 0, 0, at -2 and +2. Okay, so I lied. I think I do need to know where it crosses. So I'm going to do it the lazy way instead of going through the quadratic formula. I'm going to go in here and look at an x squared plus x minus 3. And I'm just going to zoom standard for this one. Okay, oops, graph. So it looks like it crosses between -2 and -3, and between 1 and 2. -2 and -3, so make it a little bit more out there. And between 1 and 2, so make it a little less out there. There's all sorts of crooked. Okay, so here's my global behavior. So really none of this middle stuff matters all that much. What matters is that I should have arrows really close to this and really close to this. Okay, so the reason that I was caring about where the zeros are, because it does tell me whether I'm inside or outside of that, which may matter or may not. So plus or minus 2. And then we have a vertical asymptote at x equals 1. Okay, so let's see if we can figure out. So we have an arrow here, and then we have to come down, multiplicity 1? Yes, so we have to come down and we have to sort of follow this, and then it looks like we're going to have to, we're probably just above it. So we're going to follow this shape down, and then the global behavior quits having such a strong influence. We hit this, we have to turn around and hit this, and then we have to head, since there's no more intercepts, up to positive infinity here near the vertical asymptote. This x equals 1 is also multiplicity 1, so now I have to start down here at negative infinity. And, oh, sorry for the shake. I have to cross at, what is that, at 2. And then the global behavior is going to take over, so I'm just going to start approaching this. So instead of zooming out and seeing what pretty much looks like a straight line, if we zoomed out here, the vertical asymptote would still kind of show up as a line, but the big thing you'd see is sort of a parabola shape happening. So that's kind of a weird one, just so that you know what happens if the powers get further apart. So if the top was 4 and the bottom was 1, we'd have cubic global behavior, and it could be any of those. So our big focus is the linear global behavior or horizontal global behavior, which I guess is linear too, but you can have these other things as well. All right, thanks for watching.